Hello, everybody. This is Professor Ma, and this is the sections on the derivatives and integral involve inverse trig functions. So we're going to do two things. We're going to first use the chain rule to develop the formulas for the derivative of the inverse trig functions, arcsine or cosine. Then we're going to look at the patterns of the derivative and then use that to do integrations that fit the pattern that was answer involve these trig functions. Okay, so in the picture we're going to need, and so let's, which is the sine inverse. Okay, so we're going to utilize this as a basic example how we get our answers. Okay, but recall that if I have a pair of inverse function, then the graph is symmetric with respect to the diagonal line y to x. In particular, in this picture, the most important thing is if a point, here's a point, let's say it's AB, this is the point that BA, because F inverse has to take B back to A. Okay. And the important things of it, if I draw the tangent line of F, I draw the tangent line for F inverse, and then it turns out if this slope is m, then the slope of this one is 1 over m. And this is the first important observation on the geometry. Okay, so this is what we go through this in symbols. So the slope at the point of f at the point A is the derivative of f prime evaluated at A. The slope at the point of the inverse at the point the reflection BA is its derivative, the derivative of the inverse evaluated now at B. Okay, and remember B is also f of A. So in this there is quite a few algebraic steps kind of goes around in circle, but actually that's where the trick is. Okay, so we'll go continue from these. So anyway, so in symbols, this is the slope right here, and we say it's equal to the reciprocal of the slope over here. Okay, and here is the derivations. So suppose I have a pair of inverse functions, f and g are inverse of each other's, and I take the derivative on both sides. On the left-hand side, I'm going to use chain rule. On the right-hand side, derivative of x is 1, the dx on both sides. Okay, that's why we're taking the derivative on both sides with respect to d dx. So on the right-hand side, it's 1. On the left-hand side, chain rule. Okay, is a product of the derivative of f times derivative of g. But the trick part is the derivative of f is evaluated at g of x. But g prime of x. Okay, and then it will be the derivative of f prime evaluated at g of x. Or use so I'm going to try to fix it. We'll continue. Okay, there it is. So why am I doing all this? Oh, now I'm going to set the following thing. I'm going to set g of x to be the inverse trig function outside. F of x, of course, is sine of x. So g and f is an inverse pair, right? And plugging g, I want to find the derivative of g prime of x. So if I plug it in, I get this equation, g prime of x, or arcsine derivative of that. It's 1 divided by sine, derivative of sine, but evaluated at arcsine of x. And so to do that properly, I have to call, instead of saying the derivative of sine of x, I have to say call this the derivative of sine with respect to letters y, okay, and but evaluate at y equal to cosine of x. Okay, and derivative of sine is cosine of y, and y is cosine x, so I get cosine of arc sine of x. Okay, so I get these interesting compositions as the derivative of arc sine. And this we can actually interpret geometrically. Okay, and this is a little trick. You can, it's algebraic trick. You can try yourself and then say, let's suppose I use the formula for arc cosine. Okay, similarly, I'm going to get the relationships, a composition relationship for the derivative of arc cosine. And then f of x, then it's going to be cosine of x. And the derivative of arc cosine, oops, with x, is going to be 1 divided by the derivative of cosine. Okay, except I have to evaluate these derivative at y is equal to arc cosine. Okay, and when you finish, we get this relationship. Derivative of cosine is minus sine, so I get minus sine, but evaluated at arc cosine x. So, okay, so I get these strange composition relationships, 1 over that. For the derivative of inverse trig functions. What do we do now? That has a geometry interpretation. Remember the reference triangles? Arc cosine x is an angle, theta. And there's a picture for theta. Basically, theta has to satisfy the condition its sine is x. In other words, opposite over hypotenuse is x. So this is the angle theta, and the theta is this angle. Then we know what the other side over here, the third side is. And this is the reference triangle which allowed us to read what cosine of this angle theta is. And cosine of this angle is just 1 over arc sine of 1 over 1 minus cos x squared. Okay, so this trick, it's kind of like first time when we kind of look at it, we kind of puzzle, say, wow, gee, how did that come out? Couple of things. It goes through algebra steps, and then it come out to be a compositions, and that composition can be interpreted geometrically. And we get the answer through the pictures of triangle, and that's very interesting. That's probably the first time we do this kind of algebra through pictures and come out with the answer. The second thing is notice arc cosine of x. This is a trigonometry related formula. Its derivative is a algebraic function. It crosses families. So that's interesting. And such is the case for all the other derivatives of inverse trig. And so this is the inverse trig of sine, inverse trig of cosine, inverse trig of tangent, and I gave you the pictures, and I gave you the answer for every one of them. All of them is done through the method we just described. And by the way, that's a general method for finding to computation if you need it for a pair of inverse functions. And so you take the derivative on both sides, and you get these inverse relationships of the derivatives. Okay. And in terms of the trig functions, it turns out inverse trig function, they have a nice geometric interpretation of the reference triangle. You can read out the answers, and it all turns out to be nice algebraic functions. So that's a surprise. In particular, we have the chain rule. Suppose the function u is u of x. Okay, and now I can take the derivatives. Oops. Since here's the chain reversions. Okay, this u is some kind of formula in u of x, then the derivative in terms of x, and these are the chain rule. And we're going to concentrate on 3 different forms. Okay, we're going to concentrate on particular cosine, which is the same as sine in some sense. Okay, I mean integrate. It has these forms. Derivative on top. The first of all, u prime is from the chain rule, and then the denominators. Okay, we have 1 square of 1 minus u square, and then 1 for the tangents, 1 plus u square, and for the secant is u times square root of u square minus 1. So there's 3 different patterns I want you to observe now in the denominator, because we're going to later on do integral, and we're going to use this pattern to decide which inverse trig we're going to. It's going to be the antiderivative. Okay. But first, let's take derivatives. So if I want to take tangents inverse, chain rule, so u in here is x cubed. So the derivative of this is going to be derivative of x cubed, 1 plus x cubed square, and so on. So it's a good review on chain rule for taking derivatives. The secant log, so secant inverse log of x. Secant inverse u is derivative of u is the log of x. So derivative of log of x is 1 over x. And then you have log of x, square of log of x squared minus 1. Okay, so that's chain rule for derivative. Backward. Okay, so in terms of antiderivatives, we have these relationships. Okay, notice the antiderivative of this getting between sine, getting the answer inverse sine and inverse cosine, all the difference is a minus sign. Okay, and the reason that the difference between having a minus sign become cosine inverse is basically because the difference between cosine and sine inverse are constants. Okay. So in other words, you can write the answers in this easily into. It's also correct to minus as minus sine inverse of u plus constants. 1 over same answer, derivatives wise. Okay. But for the patterns 1 plus u square, and then you will get tangent inverse. And for the pattern u times square root of u square minus 1, I get secant inverse. So in terms of antiderivative for substitutions, now we come to pattern matchings. So for example, if I want to integrate these and look at it for a while, you can break it up. Substitution doesn't work for now. Okay, so what can we do? Well, now we're going to try integration by patterns. What do we mean by this? Well, which of these patterns matches this denominator? Okay, we can convert that into that form. Square sum. Any square sum, a squared plus b squared x squared, can be switched into that form by playing around with coefficients. How? Take out the form. So I have 1 matches the 1, and then the x squared matches 4/9 x squared matches the u squared, and then it gives us what u is. U has to be 2/3 x, and that's the correct substitution. Okay. So once we put in this format, and it matches the having u set to be a linear terms, that these can match into the antiderivative of 1 over 1 plus u squared. Okay, so for any square sum in the denominator, I can manipulate into this pattern. And that's one good algebra practice to do. It's simple, but you should practice this. So now get tangent inverse of u, then put the u back as 2/3 x. Okay, so this is what I mean by pattern matching. That is, if I look at the antiderivatives of these things, it asks, and which one of these patterns fits the ones we have, and you know, it's a square sum. So therefore, it's this one right here, and then I convert into the patterns using substitution. How about this one? Well, this one fits the u prime over 1 minus u squared. How so? Well, this is because derivative of e to the 2x is 2 times e to the 2x. Okay, here. So I got 1 minus u squared. So, okay, so we say u, let's do the substitution first. Okay. U is e to the x, therefore dx is du divided by e to the x. So dx, change into du divided dx change to du divided e to the x, and cancels. That's how we change into that sine inverse antiderivative of inverse trig sine of sine. Okay, so this basically I'm saying this can be integrated, you know, using the pattern du1 minus u. And if there's a u out there, then I will use a secant. I will use the secant. Then this is carried through all the way calculations. Excuse me. Then finally, so this is what we call in mathematics. Let me go back to the formulas we have. These formulas, the basic ones I'm interested in are these 3 different types. Okay, this is what we in mathematics will call a lot of time called integration by table. That's by pattern matching. That is, you kind of match the integrand you have, and then you have there's a table that for the particular form it matches the table. You can using some kind of substitution methods to matches the table, but the table will tell you what the answer is. And there's a huge table of all different type of patterns that you can match. And these are the 3 very fundamental ones involving inverse trig functions. Okay, and from this pattern matching of doing integration, there's another 6 formulas which we call hypergeometry. Hypertrig functions. Okay. Hyperbolic trig functions. Okay. These are actually 6 functions defined by e to the x and e to the minus x, different combinations of it. Okay, and there's 6 of them. And okay, the hyperbolic sine, or is we write as SINH, called it, pronounce it as sinh. It's e to the, it's defined as these. Okay, and the hyperbolic cosine. Here, I might just show you. Okay, cosine is the sum divided by 2. And then the tangent is hyperbolic sine divided by hyperbolic cosine. You have the same reciprocal relationships, and so we define the other members of these hyperbolic trig functions in the following manner. Okay, so I got 6 functions over here. The hyperbolic. Why are they called trig functions? Well, they're not really trig functions. They're not really related to angles, but what they are related is the relationship of the derivatives in the integral patterns, very much like trigonometries. Okay, so basically, I will show you some of the relationship among these hyperbolic trig functions. And you have this similarly hyperbolic trig hexagram. If you learn tricks from me, then you know there's a hyperbolic, there's a trig hexagram that tells you all the basic relationships of the trig functions. And similarly, we have a hyperbolic trig hexagram, and we have this difference of square relationships. Very similar to trigonometries with this sum. Okay, so sine squared plus cosine squared is 1. For hyperbolic trig functions, it's difference of square. Okay, and so we have a list of formula like this. And similarly, they have a similar relationship with derivatives and antiderivative. And so they generate another list of patterns that solve equation related to derivatives. Okay, and this is as much as I'm going to say about hyperbolic trig function. We're going to deal with. Okay, and our main emphasis will be the hyperbolic sine. Main emphasis will be the sine inverse, tangent inverse, and secant inverse. Those three form to help us to do integrations and the pattern recognitions. Okay, and that's it. Bye-bye.